Open any CFD report ever written, and within the first three lines, you will find a number. Ra, the Reynolds number. Inertial forces divided by viscous forces. It tells you whether your flow is laminar or turbulent, what mesh resolution you need, what turbulence model to pick. Every aircraft, every car, every weather forecast, every blood flow simulation reports it. And almost nobody knows the man it is named after. Today we fixed that. By the end of this video, you will know who Osborne Reynolds was. The experiment that made him famous in 1883. The equation he wrote in 1895 that still runs 90% of industrial CFD, and why every fluid mechanics course in the world starts with his number. Born 23 August 1842, Belfast. Son of a clergyman who was also a mathematician, so the genes were good. But here is the surprising bit. Reynolds did not go straight to university. At 19, he apprenticed to Edward Hayes, a mechanical engineering firm in Stony Stratford, England. He spent a full year working with his hands, building real machines, before he ever stepped into a lecture hall. Then in 1864, he went up to Queen's College, Cambridge, to read mathematics. He graduated in 1867 as the seventh wrangler, meaning seventh place in the entire Cambridge mathematics tripos. That combination, workshop engineer plus Cambridge mathematician, is what made him able to do what he later did. In 1868, at age 25, Reynolds was appointed the first professor of engineering at Owens College in Manchester, what is now the University of Manchester. This was only the second engineering chair in all of England, after University College London. He stayed there for 37 years. He built the engineering department from nothing. He trained generations of students. And he conducted his most important experiments in the basement workshops of that same building. Manchester in the late 19th century was the engineering capital of the world. Textile mills, steam engines, locomotives. Reynolds was the right man in the right city at the right time. He was elected Fellow of the Royal Society in 1877 and awarded their Royal Medal in 1888. Now the headline experiment. 1883. Reynolds builds a long glass pipe and submerges it in a tank of perfectly still water. At the upstream end, a thin trumpet inlet. Behind the inlet, a needle that injects a fine streak of colored dye into the water as it enters the pipe. He opens a valve at the downstream end. Water flows. At low flow rate, the dye streak runs through the pipe as a perfectly straight line. He called that direct motion. We call it laminar. Then he gradually increases the flow rate. At some critical point, bang, the dye streak suddenly breaks up and mixes into the whole pipe. He called that sinuous motion. We call it turbulent. The transition happens, he found, at a critical value of the dimensionless ratio UD over nu of around 2000, the first quantitative law of transition. Every fluid mechanics course in the world reruns this experiment. What is the Reynolds number actually doing? Take the velocity of your flow, u, the size of your obstacle or your pipe, L, the density of the fluid, rho, the dynamic viscosity, mu. Multiply them as rho ul divided by mu. That is Re. It compares two competing physical effects: inertial forces, fluid wants to keep moving, and viscous forces, fluid resists internal shearing. When Re is small, viscosity wins. The flow is orderly, streamlines are smooth. When Re is large, inertia wins. The flow becomes unstable, chaotic, turbulent. Microfluidics runs at Re much less than 1. A swimming bacterium is at Re around 10 to the minus 4. A car at highway speed sits around Re 10 to the 7. A ship at cruise is around Re 10 to the 9. The same equation, the same dimensionless number, spans 14 orders of magnitude. 12 years after the dye experiment, Reynolds did something even more consequential. He sat down and tried to extend Navier-Stokes into the turbulent regime. He had an idea: split the velocity into a mean part plus a fluctuating part. U equals U bar plus U prime. Substitute that into the Navier-Stokes equations. Take the time average. What falls out is what we now call the Reynolds average Navier-Stokes equations, RANS. and buried in them is a new term: the mean product of fluctuating velocities, the Reynolds stress tensor. Six unknown components, only four equations. This is the famous closure problem of turbulence, and it is the reason every K epsilon, K omega, SST, and Reynolds stress model in industrial CFD exists. They are all guesses for what to put in place of that Reynolds stress. Most people only remember Reynolds for the number, but there is more. 1874, the Reynolds analogy. The connection between momentum transfer and heat transfer in a turbulent boundary layer. Heat exchanger design still relies on this. 1886, the Reynolds equation for lubrication. He explained Beauchamp Tower's bearing experiments using a thin film approximation. Tribology, the science of bearings and lubrication, dates from that paper. He also worked on cavitation, explaining why ship propellers suddenly lose efficiency at high speed. He studied granular flow and dilatancy, why a bag of sand expands when you squeeze it. He even contributed to the theory of group velocity in dispersive waves. The Reynolds number is the headline, but the body of work is wider than most engineers realize. One detail that surprises people: Reynolds himself never used the term Reynolds number. The name came later. In April 1908, at the International Congress of Mathematicians in Rome, the German theorist Arnold Sommerfeld delivered a paper on the hydrodynamic explanation of turbulent flow. In it, he wrote, in German, a pure number, which we shall call the Reynolds number. That phrase attached to that quantity, stock. By the 1920s and 1930s, the term was universal. Reynolds lived to see this. He retired from Manchester in 1905, was in poor health, and died in February 1912 in Watchet, Somerset, less than 4 years after Sommerfeld coined the name. He never wrote the word himself. Fast forward to today. Every commercial CFD code, Fluent, Star CCM Plus, CFX, OpenFOAM, uses Reynolds averaging as its workhorse approach for industrial problems. Roughly 80 to 90% of all industrial CFD core hours in 2026 are RANs. That means roughly 80 to 90% of industrial CFD is direct application of Reynolds' 1895 paper. The Reynolds number itself is reported on the first page of every CFD report ever written. It sits in the dimensionless inputs of every wind tunnel similarity study, and it shows up in every undergraduate fluid mechanics course in the world, usually in week 1 or 2. 130 years after the 1895 paper, his framework is still the foundation. That is not a common thing in engineering. Three things people get wrong. 1. Reynolds did not discover turbulence. Turbulence had been observed for centuries, sketched by Leonardo da Vinci 400 years earlier. What Reynolds did was give it the first quantitative criterion. 2. Transition is not exactly at Re equals 2300. That number is a textbook simplification. The modern statistically defined value is 2040, plus or minus 10, from Avila and colleagues in Science in 2011. Above about 4000 turbulence is sustained. Below about 2000 it eventually decays. 3. RANS is not old-fashioned. Despite all the LES and DNS and machine learning, RANS still does roughly 8 to 9 out of every 10 CFD jobs in industry. Reynolds' 1895 framework is not going anywhere. 184 years since he was born. 130 years since the RANS paper. The dye experiment is still rerun in every undergraduate fluid mechanics lab. The Reynolds number is still the first checkbox on every CFD problem. 85% of industrial CFD still runs on his 1895 framework. The original 1883 apparatus still sits at the University of Manchester and still works. That is what scientific durability looks like. The Manchester engineer with the workshop hands and the Cambridge mathematics. Born in Belfast in 1842, died in Somerset in 1912. Still running every CFD simulation in the world. Thanks for watching CFD Toolbox. If you want more CFD content, hit subscribe and check out my other videos on the channel.